Hello everyone. This is Indrani of Institute of Aeronautical Engineering College. So we are going to discuss on the subject of IC applications. In that IC applications, today we are going to discuss the topic on the DC characteristics of the operational amplifier. First, what are the DC characteristics? In the previous class, I have explained regarding the what is the ideal and practical characteristics of the op-amp. So, by briefing again about the ideal and practical characteristics of the op-amp, let us go to the today's topic on the DC characteristics of the operational amplifier. So, here mainly under the DC characteristics, we are discussing regarding the input bias current, input offset current, input offset voltage, and thermal shift. So these are the main four DC characteristics of the operational amplifier. So in the opposite to these DC characteristics, we are having the AC characteristics also. Here basically, if you see what is this DC characteristics, what is the AC characteristics? Generally, DC characteristics means if due to the DC supply voltage under the absence of the AC input signal, under the absence of the AC input signal for the operational amplifier, I need to get the output voltage value should be 0 for the ideal operational amplifier. So, for the operational amplifier, if the AC input signal is, suppose here for the operational amplifier, for the op-amp, as I discussed with you in the previous classes, so in the operational amplifier, basically we are giving the two types of supplies for the operational amplifier. One is the AC input for the inverting and non-inverting terminal of op-amp, and second input is a DC power supply, DC supply. What is the DC supply? The DC supply is plus VCC and minus VEE. What is the purpose of the DC supply? The purpose of DC supply is here to switch on the operational amplifier. We have to give the continuous DC supply. By giving the continuous DC supply for the operational amplifier, then only based on the input signal of AC input signal, certain amount of output waveform we can get. First, to start the operation with respect to operational amplifier, initially I need to give the DC supply voltage value for the operational amplifier. Okay. So, coming for the DC characteristics of the op-amp. The DC characteristics of the op-amp is why we are discussing regarding this is for the operational amplifier. Suppose if I am not giving any AC input signal for the operational amplifier, then at that time my output signal of op-amp should be 0. Okay. Output signal of op-amp should be 0 if I am not giving any AC signal. But here, due to the DC supply voltages, even if I am not giving any AC input signal also, I will get some output voltage. Whatever that output voltage is there, that output voltage is the erroneous voltage. Erroneous voltage means here without giving any AC input signal for the operational amplifier, based on the DC supply voltage value, I am getting certain amount of the output voltage. So that output voltage is called as the erroneous output voltage. To get the output voltage, the possibility to get the output voltage under the absence of the AC signal is, it may be due to the input bias current, input offset current, input offset voltage and thermal shift. Because of either of the properties or a combination of all these voltages and currents, I can get some output voltage across the operational amplifier. So first let us see what are the characteristics for let us review about the op-amp ideal characteristics. So if I consider the ideal characteristics of the op-amp, the equivalent diagram for the ideal op-amp is, it is having the infinite input impedance, right? So, and here the output impedance of the op-amp equal to 0 ohms, Okay, and here what are these terminals are there? This is the inverting terminal. This is the non-inverting terminal of the op-amp. So according to the ideal characteristics of the op-amp, the input impedance value is infinite input impedance can be present, and the output impedance value is 0. Even if you see the internal diagram of this op-amp, we are having the output impedance value equal to 0 in this location. Next, open loop voltage gain. The open loop voltage gain of the operational amplifier is infinity is the open loop voltage gain. So here, if the difference between the input voltage value, the difference between the non-inverting and the inverting input voltage value equal to 0 volts, at that time, I need to get the output voltage value equal to 0 volts. For example, suppose if I am giving the 5 millivolts is the input I am giving for the non-inverting terminal of op-amp, and 5 millivolts is the input I am giving for the inverting terminal of op-amp. Both the input signal voltages are 5 millivolts and 5 millivolts. So these are the AC signals I am talking. Okay. So this is the AC input signal which is having the amplitude of equal amplitude. Otherwise, even if you give the DC supplies also, some plus 5 volts and plus 5 volts I am giving for both the input terminals of op-amp, I need to get the output voltage value equal to 0 for the ideal case. So this is the fourth property of the ideal characteristics of the op-amp. Next, the bandwidth is infinity. What is meant by bandwidth is infinity? If the bandwidth is more, the bandwidth is infinity means if I draw the frequency versus gain graph, for all the set of frequency ranges, the gain, the voltage gain should be constant. What is the significance of this bandwidth? Why the bandwidth should be a infinity or a high value means here the bandwidth signifies for all the set of frequencies. All the set of frequencies means whether it is the audio frequency or radio frequency, for whatever may be the input signal frequency, the output voltage value should be a constant. Okay. So the gain of the circuit should be constant. It should not depend on what is the input signal frequency. Okay. So if it is maintaining the constant gain, then it signifies that the bandwidth of the op-amp is infinite bandwidth. Next, the Cmrr. This is one of the property we will discuss in the operational amplifier. As I discussed with you in the previous class, Cmrr is the common mode rejection ratio. This common mode rejection ratio is represented as Cmrr equal to differential gain. The differential gain by common mode gain. Okay. So here this common mode gain value equal to 0. Okay. And the differential gain, then the resultant Cmrr value is infinity is the Cmrr. For the ideal op-amp, the Cmrr is infinity. Next property is slew rate. What is a slew rate here? For the ideal op-amp, it should produce a change in the output voltage instantaneously with the change in the input voltage. If the input voltage is changing from 0 to 1 or 1 to 0 simultaneously without any lag, I need to get the simultaneous change in the output voltage of the operational amplifier. Okay, so generally the slew rate value is infinity. Slew rate value is infinity means the time delay is 0. Okay, the slew rate value is infinity means the time delay is 0. Slew rate and time period, both are inversely proportional to each other. So here the slew rate is inversely proportional to the time delay 1 by t. So here there is no lag should be there. At the time the slew rate value equal to infinity is the slew rate value has to be maintained. Now coming for the practical operational amplifier. For the practical operational amplifier, if you observe here for the ideal op-amp I have represented ZA, the input resistance is infinity is the input resistance or input impedance I have represented. Okay, so but for the practical op-amp, it consists of the input impedance which is somewhat high value, not the infinite value. Next, for the ideal op-amp, the output impedance Z0 is equal to 0, but practically it is having certain value. Okay, so that is a low value will be present. Okay, so if you see what is the practical characteristics of the op amp. So the practical characteristics of op amp is the input impedance value ZA is in the order of mega ohms, it is there. The Z0 value is in the order of ohms will be there, and the voltage gain value is a high voltage gain value. Sorry. Yeah. Next property is the output offset voltage should be low value. Output offset voltage should be low value. We will go through the what is the output offset voltage. Next, the bandwidth is, we cannot get the infinite value in the bandwidth. We can get the high bandwidth value. Next, the Cmrr. The Cmrr value is a high value, not infinity. And the slew rate value is a high value, not the infinity. Okay. So these are the practical characteristics of the operational amplifier. Sorry. Yeah. Now, let us go for each and everything here. The input bias current is represented by the base current IB, and input offset current is represented as IOS. Input offset voltage is represented as VIOS, and thermal shift is one of the factor. Now, let us go for here, whatever these parameters are there. Because of all these parameters, for the given DC supply voltage, I am getting the error in yes output voltage. In the ideal case, I should get the output voltage value equal to 0 is the output voltage value has to be present. Okay. So whatever the output voltage we are getting because of all these things, the output voltage is represented as a output offset voltage, VOSS. So first let us talk it with respect to the input bias current. What is the input bias current? The input bias current is a average of the currents entering into the inverting and non-inverting terminal of the op amp. It is the average of the currents that are passing through the inverting and non-inverting terminal of the op amp. So for the operational amplifier, whatever the current that is passing through the inverting and non-inverting terminal of op amp is there, that is called as the average of those currents is called as input bias current. The value of the input bias current is of the order of, for the 741 op amp, the order of the input bias current is 500 nanoamps. If you consider the corresponding transistor is the field effect transistor, it is having the input bias current is that the average value of the current is 50 picoamps is the currents it is having. Okay. So here, for the ideal operational amplifier, we know that the input impedance of the ideal operational amplifier is infinity. Input resistance or input impedance value equal to Z equal to infinity. At that time, if the input impedance is infinity means, then the operational amplifier should not draw any amount of current from the inverting and non-inverting terminals of the operational amplifier. Okay. But practically speaking, the resistance value is not infinity. Somewhat it is a high value. So definitely it will draw some amount of the current. Because of that current, I can get certain amount of the output voltage. Okay. So, yeah. So here, the current that is passing through the inverting and non-inverting terminal of op amp base currents is represented as IB minus and IB plus here. Okay. So next, here generally the IB, let us consider in this case both the transistors. Generally, what is the internal diagram of op amp is? The op amp is having the 4 stages. So first stage is dual input balanced output, dual input unbalanced output. Third stage is a level shifter, and fourth stage is the output stage. So here the differential dual input balanced output differential amplifier is internally it is having the two common emitter configuration circuits which are cross coupled to each other. So if I consider both the transistors are symmetrical with respect to each other, at that time the IB plus and IB minus, the base currents that is flowing through entering into the transistors are equal. IB plus and IB minus both are equal. Okay, but we cannot get the corresponding equal amount of currents, we cannot get, but in the input bias current I'm assuming that the both the currents IB minus and IB plus both are equal. At the time, yeah. So here, yeah, by considering the IB equal to the input bias current equal to average of the input base currents IB plus IB minus by 2. So if you consider this circuit here, in this circuit, I am taking the inverting amplifier itself. In this inverting amplifier, by taking the input voltage value equal to 0, at the time, the current is also 0. Okay, and these are the IB minus and IB plus which are entering into the input of the corresponding operational amplifier. Okay, so now under the absence of AC input voltage also, some amount of IB minus and IB plus currents are entering into the operational amplifier input. Okay, these currents are the DC currents that is entering into the operational amplifier. So due to these DC currents, definitely I can get certain amount of the output voltage, right? Certain amount of output voltage I will get. So here, what I need to do here, if the input is 0, output should be 0. But even though due to these these bias currents, I am getting certain amount of the output voltage here. So I should make the output voltage value equal to 0. What is the amount of output voltage I can get is output voltage V0 equal to the current that is flowing through the feedback resistor into the concerned resistance value. Okay, the current that is entering into the feedback resistance into that concerned resistance value. How you got this expression? Here if you observe here, the current through this AC input signal equal to 0, I1 value equal to 0. Okay, so then what is the amount of current that is passing through the feedback resistance? Same IB minus is the current passing through the feedback resistance. So this current is taking the direction like this. So due to this one, we are getting the output voltage. Current entry path is positive, exit path is negative. Based on this, output voltage equal to IB minus into RF. So this IB minus into RF, this is the erroneous output voltage we are getting under the absence of the AC input signal. Okay. So now you understood one thing. Here, this is the error voltage I am getting here. Now I need to compensate this error voltage. How to do compensation? Compensation means first initially on or giving before switching on the circuit here, first I need to check whether any output voltage is present or not under the absence of AC input signal. If the output voltage is present at the time, I need to compensate the output voltage, means I need to make output voltage V0 value equal to 0 volts. To say that, here I am taking one compensation for the input bias current. I need to make the erroneous output voltage value equal to 0. So that's why some precaution I need to make. Okay. So some precaution I need to make. Whatever the previous slides are there, I discussed with you previously. Yeah. So that's why I'm skipping this one. So here, yeah, coming for this one. Now here, to compensate the erroneous output voltage here, I am taking one compensation resistor. That compensation resistor is represented as a R comp. Okay, where I am keeping this resistance is, at the non-inverting terminal of op-amp, I am connecting this R compensation resistor. Okay, now the next step is I need to find what is the amount of resistance, what is the amount of R compensation resistor I need to consider. Okay, so that R compensation value is required for me. So to find what is the R compensation value here, first what I am doing is just apply the KVL to this loop. Okay, in this dotted line representation, yeah, in this dotted line representation, just apply KVL to this loop. What is the KVL equation for this one? Here, across the R compensation resistor, I have represented the drop across this R compensation is V1 is the drop across the R compensation. The drop across this one is minus V1 because I am taking the current entry path is like this and exit path is like this. So, entry path I need to take is plus. Okay. So, from positive to negative, there is a voltage drop is there. So, it is represented as a minus V1. Next, plus the voltage between these two nodes. What is the voltage at these nodes? According to the ideal characteristics of op-amp, the difference between the inverting and non-inverting voltage value equal to 0. So, that's why here VD value is represented as a 0. So, plus 0. Okay. Apply here. So, plus V1 and minus V0 equal to 0. Here across the output voltage, this is the positive terminal and this is the negative terminal. So here if I simplify this one, I am getting the V0 value equal to V1 minus V2, right? V0 equal to V1 minus V2. After this one, first I need to find what is the V1 value and what is the V2 value is required. Then I can find what is the R compensation value. So for that one, what I am doing is first separately I am finding what is the V1. What is V1 here? V1 is nothing but voltage drop across the R compensation resistor. What is the voltage drop across the R compensation resistor? The current passing through this R compensation resistor into that concerned resistance value, that is IB plus into R comp equal to voltage drop across R compensation resistor. So from this one, IB plus equal to V1 by R comp, right? V1 by R comp. Later I need to find what is the IB minus value. Here IB minus equal to, right? IB minus equal to, here what is the value of IB minus? Here if I see the current passing through this feedback resistor is RF and the current passing through the resistor R1 is I1 here. Then by applying the KCL to this node, some of the currents coming towards this node, equal to some of the currents leaving away from that node. Based on that KCL here, Kirchhoff's current law, IB minus is current leaving that node and I2 and I1 are the current coming towards that nodes. So based on this one, I2 plus I1 equal to, what is the I2? I2 is nothing but current that is passing through the feedback resistance RF. So I2 equal to simply here what I am taking here, this I2 is nothing but V1 by RF. Here V1 by RF is here, yeah, in two forms I can take what is the V1 and RF. Here according to the ideal operational amplifier, the difference between the input voltage value equal to 0 means the difference between the input voltage value equal to 0, at the time if I see this circuit here, the voltage at this node equal to V1 is the voltage at this node. Then what is the voltage at this node to make the VD value equal to 0? The voltage at this node is also equal to V1. Okay. So then what is the current here? Current I2 equal to V1 by RF. Right? Current equal to I2 equal to V1 by RF. Similarly, current I1 equal to again V1 by R1. With respect to this node, I am calculating what is the currents of I2 and I1. Okay. So, V1 by R1 plus V1 by RF. Now, just to simplify this equation. So, if I simplify this equation and do LCM here, then I am getting that V1 equal to R1 plus RF by R1 RF. Okay, what is this expression? This is the expression for the IB minus. Right, this is the expression for IB minus. Here I got IB plus and here I got IB minus. So according to the transistor, at the both inverting and non-inverting terminal of op-amp, the corresponding currents passing through the both inverting and non-inverting terminal of op-amp equal to both are equal. Just I am taking that assumption. With that assumption, So here this current expression is equal to this current expression. Then if you see here IB plus equal to IB minus here, then what will happen with respect to R comp here? So here you can get the expression which is of the form V1 by R comp, right? V1 by R comp equal to V1 into R1 plus RF by R1 RF. Okay, if I compare these two resistances values here, the resultant is R comp equal to parallel combination of here R1 RF by R1 plus RF. So here this is nothing but a parallel combination of R1 and RF itself, R1 and RF, right? So this is the R compensation resistor. Why we are taking this R compensation resistor? Just to compensate the effect of the input bias current. Due to the input bias current under the AC signal value equal to 0, I am getting the output offset voltage, not output voltage, output offset voltage I am getting here. Okay, to compensate that output offset voltage here, just I have added one resistance for the non-inverting terminal of the op-amp. That resistance is called as a R compensation resistor. By adding this resistance, what is that resistance value? It is a parallel combination of R1 and RF value. So if I keep this resistance resultant value of R1 and RF value here in the R compensation resistor, then I can make first initially the output voltage value equal to 0 for the input bias current. Okay, so this is about the input bias current, right? So if you have any queries, please send the message, I will give the reply. Okay. The next DC characteristics is input offset current. What is this input offset current? So in the previous case of input bias current, we have assumed that both the IB plus and IB minus both are equal. Okay, IB plus and IB minus both are equal. What is IB plus and IB minus? IB plus and IB minus are the base currents of the inverting and non-inverting terminal of the operational amplifier. Okay, base currents of the internal transistors, two different transistors. And in the previous input bias current, we are assuming that both the currents are equal. But practically speaking, there is no two transistors are said to be equal. Even in your lab experiments also, if I distribute the corresponding same type of transistors, so BC107 transistors, if I take 100 number of BC107 transistors, for 100 number of transistors, I will get different values of the currents and the corresponding voltages. No two transistors are said to be symmetrical. So that's why here, by considering the practical consideration, so if the transistors are not symmetrical with respect to each other, at that time, IB minus is not at all equal to IB plus. So in the previous input bias current compensation, by taking the assumption that both the IB minus is equal to IB plus, we have set the corresponding compensation resistor or compensation resistor we kept. But practically speaking, the IB minus is not at all equal to IB plus. So whatever the difference in the currents are there, the difference in the currents is called as a input offset current. So if you see the definition here, this is the algebraic difference between the currents entering into the inverting and non-inverting terminals of the op-amp. So here that is called as a input. The difference here previously average. Now we are taking the difference between the IB plus and IB minus. Yeah, please observe the difference. Now what is the difference will be there? The difference is of the order of 20 to 60 nanoamps. Okay, 20 to 60 nanoamps. So due to this current, definitely, even if I am having the input voltage value, the input signal voltage value equal to 0 also, due to the difference in the corresponding current, I can get certain amount of the output voltage. Okay, this output voltage is due to, this output offset voltage is due to input offset current. That is due to the difference between the bias currents of the difference between the base currents of IB minus and IB plus. Okay, so now the next step is, here also we need to introduce some compensation for this. Okay, Here also we need to make some compensation for this. Now here, the difference in the currents is represented as modulus of IOS equal to IB plus minus IB minus. This is the input offset current. So due to this input offset current, now here also I need to due to this offset current, I need to find what is the amount of output voltage. To find the amount of output voltage here, same like a previous thing, by taking the OR compensation resistor, this OR compensation resistor is just to compensate the input bias current. This compensation resistor is for the input bias current compensation. Okay, so first I am taking one compensation resistor of OR comp. Now first find what is the output voltage due to the corresponding difference between the corresponding bias currents or base currents. Okay, so here to find this proportionality, what is the relation between this voltage and this current here, I am doing the derivation of first finding the what is the output voltage. So here first to find the output voltage, the first thing is find what is the this voltage across the OR comp resistor. V comp equal to current passing through this OR comp resistor into this resistance value. So that's why V comp equal to IB1 into OR comp has been given. Okay, so now first I want to find what is the output voltage. Okay, what is the output voltage? So for this output voltage here, what I am taking is here. If you see, for a better understanding, first I need to bring what is the output voltage. To find the output voltage is taken as V0 equal to I2 into RF. The current passing through this feedback is I2 I am taking here, I2 into RF minus V comp. How you got the V comp? The difference between the input voltage values of the inverting and non-inverting terminals of op amp equal to 0. So if the voltage drop across this resistor is V comp, then what is the voltage drop at this point? This is also V comp itself. Is it right? V compensation itself. So based on that point, V0 equal to I2 into RF minus V comp has been considered. Okay, so from this expression, what is the I2 into RF minus the V comp has been replaced by the above expression. The V comp has been replaced by the above expression. Now, what is the current I2? What is the current I2 here? I2 equal to, according to the KCL equations, I2 equal to sum of the currents coming towards that node equal to sum of the currents leaving that concerned node. Okay, just apply KCL to node of A. Okay, just apply KCL to node of A. Then current coming towards this node equal to I2 and I1. Current leaving this node is IB2 is the current leaving that node. Now based on the KCL here, Kirchhoff's current law here, I2 equal to IB2 minus IB1. Now coming for this IB minus I1. So what is I1 here? I1 is nothing but V compensation resistor by R1. Right? I1 equal to V compensation resistor by R1. Yeah. So here, if I substitute this equation, here what is V comp here? V comp equal to IB1 from the above expression. V comp equal to IB1 into R comp by R1. This is the equation for I1. So Asterisk equation has been substituted in the below expression. Okay, is it clear? So like this I am finding what is the I2. Now if I substitute this I2 in the below equation, okay, if I substitute this I2 in the below equation, then I will get entire currencies in terms of IB2 and IB1, right? So let us see the simplification part. Later, after substituting, I am getting the equation of the form like this. Now if you see the OR compensation, in the previous input bias current, we know what is a OR compensation resistor. OR compensation equal to parallel combination of R1 and RF. So R1 RF divided by R1 plus RF, right? So if I substitute this equation in this, if I replace the OR comp by this relation, and if I simplify this equation, then I will get the expression as the corresponding the R1 RF terms. Few of the terms gets cancelled out. Just to do small simplification, replace this or compensation by R1 RF by R1 plus RF. Then if I substitute this equation, then I can get V naught equal to RF into IOS. RF into IOS. So here the difference in the how you got this IOS here, after simplification of the previous equation, I am getting V naught equal to RF into IB2 minus IB1, where IB2 minus IB1 is nothing but the difference between algebraic difference between the bias currents is, it is nothing but IOS. In the previous expression we have seen it, right? So from this expression, we can tell that to make the output voltage value as the low value, I need to make the output, this is the offset voltage, output offset voltage as low value here. Then definitely if I take RF value is low, I can get output voltage value equal to low. Okay, but can we take the RF? What is that RF? RF is the feedback resistance. RF is a feedback resistance. Can I take the feedback resistance as low value? Absolutely no. Why? Because for the operational amplifier, the input impedance of operational amplifier is infinite input impedance, or for the practical it is having the high input impedance is there. So the feedback resistance also should be in the order of the high input impedance itself, because the feedback resistance effect will be present on the input impedance. If RF value is high and RA value is high, then only I can get the overall input impedance of op-amp value equal to high. Okay, suppose if the input impedance of op-amp RA value equal to high value and the feedback resistance value equal to low value, then due to the parallel combination of the input resistance and the feedback resistance, I can get the low value itself, right? So, but I should keep for the operational amplifier, the input impedance of op-amp should be a high value should be present. So, how to make this compensation? How to make this compensation is, here definitely I need to maintain the feedback resistance value is high. Then only I can get high amount of output voltage gain also. So, to maintain this feedback resistance as high here, we are taking some compensation we are using. What is the compensation we are using is, we are using the T type of network, right? T type of network. In this T type of network, the T type of network we are taking is, this is the RT, RS. Okay, this is the T type of network. In this T type of network, if I convert this T type of network into pi type of network, the pi type of network is represented in the dotted lines like this. Okay, pi type of network is represented as a dotted line like this. What is the advantage of this type of T type of network here is, from the input side, the corresponding the feedback resistance RF value is high and R1 value is also high. Resultant input impedance of op-amp is high value only I can get. But here if I see from the output side, from due to for this dotted line, if I consider what is the output impedance, here the output impedance of this dotted line resistance network is low. Output impedances can be present from this point to this point. Okay, low output impedance is present from this point to this point, but at the input side I am having the high input impedance. What is the impact of this? What is the impact of this is, previously you have seen, we know that V naught equal to IOS into RF, like that we have seen the expression. By keeping this pi type of network like this, I can get V naught equal to RT plus 2 RS into IOS, like this I can get. Okay, so what of this resultant value is, this resultant resistance value is low value compared to this feedback resistance value, RF value. But from the input side I can get the high input impedance, and from the output side I will get the low impedance value which is short circuited to the ground. Okay. So what is the RT and RS I need to consider? What is the RT and RS I need to consider is here. Whatever the explanation I have given for you, same thing has been mentioned. Okay. So see. So here, what is the RT and RS I need to consider is here. RT value. First, we need to choose the RT value. The RT value is very much less than half of the feedback resistance value. Like this, we need to choose the corresponding RT value. Okay. RT value we need to choose. What is the relation between these RF, RT, RS, all these things is here RF equal to RT square plus 2 into RT RS by RS. Just in the network theory, you have studied through the T to pi conversion and pi to T conversion. Yeah. So just take this network and simplify, then definitely you will get the answer as RF equal to, this is the combination, I will get it. Okay. So to find what is the RT, I have set it the RT value. RT value is half of the corresponding feedback resistance value I have set it. Now I need to find what is the RS value. To find the RS value here, just make the product here and simplify this expression. Okay. So if I simplify this expression, I am getting the RS value equal to RT square by RF in minus 2 into RT. Okay. So this is the RS value I need to consider. Okay. And this is the RT value I need to set here. Okay. So this is the compensation with respect to the input offset currents. Yeah. This is a till now with respect to currents we have discussed regarding the input bias current and input offset current. Two types of currents we have discussed. Now let us go for the third property is the input offset voltage. What is the input offset voltage? The input offset voltage is generally till now we are telling that for the operational amplifier. Yeah. For the operational amplifier, the difference between the input voltage value equal to the corresponding difference in the input voltage value equal to 0 for the operational amplifier. But practically speaking, there is a certain amount of difference in the voltage will be present. Okay. So the difference in the voltage is represented as a VIOS. Okay, VIOS. Even if I am not giving any input signal, because of the difference in the voltage values, I can get certain amount of the output voltage. Okay, that output offset voltage, let us discuss. So here, why this thing is happening here? Because of the DC supplies, completely that is due to the unbalance between the internal diagram of the operational amplifier, because there is so many stages are there with respect to operational amplifier. Okay, because of the unbalance, perfectly we cannot get a balanced type of circuit. Definitely there is some unbalanced type of thing will happen. So okay, because of that unbalance and because of this DC supplies here, even if I am giving the input voltage value equal to 0, I won't get output voltage value equal to 0. So because of this difference in the voltage, I will get the output voltage is of the order of, for the 741 op amp, I will get 6 millivolts is the output voltage. Here it is represented as 741C. What is the C represents? It is the commercially graded operational amplifier. Okay, commercially graded operational amplifier. Now here, with respect to this one, here, if I see what is the output voltage, the output voltage equal to, here for this one, I am taking a small derivation. So here, with respect to the corresponding, if I am taking this inverting amplifier, for this inverting amplifier, what is the expression for gain? Gain V0 equal to 1 plus RF by R1 into Vi. Okay, 1 plus RF by RA into Vi. Right. So, if the difference between the input voltage value equal to 0, at the time, whatever this voltage is there, what is the voltage here? If I am not giving any input signal, the difference in this voltage value is nothing but the voltage across this resistor R1 also. right? Because here, if you see, the voltage at this point is, I'm not giving any input signal for this one, yeah, and here there is a node is represented as V2 here. So here V2 VOS equal to V2 minus Vi. If I take Vi value equal to 0 or VOS equal to Vi minus V2. If I take modulus. So if I take Vi value equal to 0, I will get V0 s equal to simply V2 itself. Okay, that V2 is nothing but the voltage across this resistor R1 itself. So here, based on this expression, I can rewrite this equation as 1 plus Rf by R1 into V2, which is of equal to 1 plus Rf by R1 into VOS. So here I am getting the output voltage equal to, this is the output voltage. So here I need to compensate this this input offset voltage also. And this input offset voltage depends on the temperature parameter. Okay, this input offset voltage depends on the temperature parameter. Now I need to compensate this one. How I need to compensate this one is, yeah, whatever the previous derivation I did, same thing has been mentioning here. Okay, nothing is different. So here, yeah, this output offset, yeah, this is the final expression I got. Now this input offset voltage also I need to compensate. Okay, so yeah, this is about the input offset voltage. So I need to make the compensation for this input offset voltage. So let us see the next property, the total output offset voltage. What is the total output offset voltage? This total output offset voltage is nothing but output offset voltage due to the input bias current and input offset. We are having the two offsets, but one is the input offset voltage and input bias current and input offset current. So because of the offsets, input offset voltage and input offset current, whatever the output voltage I am getting here, I am representing the output voltage as summation of output voltage due to the input offset voltage and input bias current. Okay, so here what is the compensation I need to make? What is the compensation I need to make is, generally for the operational amplifier, we are having the 8-pin op-amp. So out of that 8-pin op-amp, the first and fifth pin are the offset null pins. To rectify this total output offset voltage, I will take some potentiometer. This potentiometer I am taking is 10 kilo ohm is the potentiometer resistance value. Just by adjusting this resistance value, till where I can adjust, till I am getting the output offset voltage equal to 0, I will adjust this resistance value. Using the potentiometer, I will adjust the corresponding resistance value. At some particular point, I will get the total output offset voltage value equal to 0. That is a nullification with respect to this total output offset voltage, right? So, and the next thing is, the last property here is the thermal shift. What is this thermal shift? Thermal drift. Thermal drift. Thermal means it related to temperature. Okay, related to temperature. So generally, whatever the input offset voltage, input bias current, input offset current, all depends on temperature, supply voltage changes, and the corresponding time duration. Okay, now in the thermal drift here, I am talking with respect to what is the dependency of the corresponding input offset voltage bias and the input offset currents on the temperature here. So here, this with respect to input offset voltage, the thermal voltage drift is defined as average rate of change of input offset voltage per unit change in the temperature. So for every degree centigrade of temperature, how much the corresponding voltage change, the input offset voltage is changing, I am finding here. That is called as a thermal voltage drift. So that's why it is represented as delta V in by delta T. Delta V in is nothing but it is the input offset voltage. Delta T is a change in the corresponding temperature. Okay, so it is having the units of millivolt per degree centigrade. Similarly, thermal drift in the input offset current. Thermal drift in the input offset current is delta IOS by delta T. So here it is represented having the units as picoamp per degree centigrade. For every 1 degree rise of temperature, the corresponding input offset current increases by the factor of picoamps. Okay. Similarly, this is a relation which is showing the relation thermal drift in the corresponding input bias current. Okay. So here these are the how these things are changing with respect to temperature. Suppose just imagine that for the operational amplifier at 25 degrees centigrade of room temperature, I have stabilized the corresponding, I have compensated all the things, the input offset voltage, input bias current, input offset, all the offset voltage and currents I have compensated. Even though if the room temperature has increased from 25 degrees centigrade to 35 degrees centigrade, due to this 10 degrees rise of temperature, all the offset voltage and currents gets changes. If these things are changing, even if I am previously made the output value equal to 0 also, because of the rise in temperature, I can get the error in its output voltage value. Then what is the alternative? What is the alternative is in the fabrication of the operational amplifier, internally in the op-amp, while doing the fabrication, what I need to make it out is, I need to separate all the components. I need to arrange some space. And at the same time, second thing is, I need to provide some cooling effect for the operational amplifier. So that's why for all the electronic systems are working under the AC conditions, because your AC can maintain the room temperature value equal 25 degrees centigrade. Okay. So by keeping the room temperature as a constant, then I can get some ideal values. There is a possibility to get the ideal values. Yeah, as I told you, some other characteristics is CMRR, common mode rejection ratio. In the previous class, we have seen common mode rejection ratio is defined as the different ratio of differential gain to the common mode gain. So that's why CMRR equal to ADM by ACM. That is in terms of dB is 20 log of ADM by ACM. Okay. So and for the practical op-amp, generally CMRR should be a infinity value, because ACM value equal to 0. So CMRR should be infinity. Practically I will get the CMRR value is in between 60 dB to 120 dB. So next thing is power supply rejection ratio. Here the corresponding internal diagram of op-amp is depends on what is the corresponding, they are sensitive to the supply voltage. Whatever the internal circuit is there, those circuits are very sensitive to the supply voltage variations. So the supply voltage always should be maintained as, it should have a low amount of noise and good regulation characteristics. Means here the supply voltage should be maintained as a constant supply voltage has to be maintained. Otherwise, due to this thing also, here your device becomes sensitive here. Okay, and we can get some erroneous output voltage. So here that the sensitivity of the op-amp with respect to power supply is represented as a power supply rejection ratio, PSRR. Okay, or supply voltage rejection ratio, SVRR. So here the PSR or PSRR is represented as PSR equal to 20 log of 10 log of PSRR base 10. So what is this dependency is, suppose if there is a fluctuations in the power supply, okay, suppose if there is a 10 microvolt change in the power supply voltage, there is a fluctuations is there, then at that time for the I will get the PSRR value equal to, for with respect to 1 volt, if I am getting the power fluctuations 10 microvolt, it's a 10 microvolt is very less, but according to the power supply rejection ratio, 1 volt actual supply voltage by 10 microvolt is nothing but 10 power 5. So power supply rejection ratio factor in disperse is 100 dB. Means 100 dB change I can get with respect to, if there is a change in the supply voltage, I can get a suddenly 100 dB change in the power supply I will get with respect to operational amplifier. Yeah, these are the two more extra characteristics. Yeah, so these are about the DC characteristics of the operational amplifier. Yeah, so in the next class, let us continue the corresponding AC characteristics of the operational amplifier. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.